Hi, everyone, and welcome to the second session of the day. My name is Nihal Munir, and I'll be your moderator. So, as always, I want to answer some questions and set some ground rules before we start. Number one, the most asked question, will we be getting a PDF of the lecture? Well, if you received the PDF from us, if we got the speaker's consent, we will be sending that to you. If we didn't send it, then we did not get the consent. So please don't ask this question. If we have it, we will send it to you. Number two, about the attendance. We are monitoring the Zoom sessions and the YouTube live. So yes, we are taking all your attendance wherever you're attending from. So again, please don't ask this question. All the questions on the Q&A and YouTube live should be related to the technical content of the lectures. Any administrative questions, please direct those to the Facebook group. So it's easier for me to filter and ask your questions, and we can deliver something informative for you, please. Last but definitely not least, keep the chat area professional. Any irrelevant comments won't be well received, and it might jeopardize your involvement in the internship. Thank you so much. So without any further ado, let me introduce our speaker for the day. Our speaker is Aaron Burton. Aaron's career has been focused on the completion of shales and similar unconventional plays that require multi-stage hydraulic fracturing. In 2015, Burton started Unconventional Oil and Gas Training, UOGT, a company specialized in training and consulting for unconventional multi-stage completions. He also provides in-house and video-on-demand training courses and performs projects including market studies, due diligence, reports on specific tool segments, and other projects. He also remains an active instructor and a participant in the industry organization. Aaron, thank you so much for joining us today, and over to you.
Thank you, Nihal. Yeah, hello, everyone. This is fantastic. I've been on several Zoom meetings so far, but as of right now, we're almost at 800 people, so nothing even close to this capacity. So it's really phenomenal what technology can bring to us, even when we're not really free to travel. So yeah, let's jump right in. So first off, this is a very quick presentation. So be sure to check out my additional resources at uog.training. A lot of free material as well, additional material that we won't have time to cover today. And then also there's a free video blog, a free training course, and also a very deep discounted paid course as well right now. And also, especially since some of you are attending by YouTube right now, be sure, if you want to keep up with the video blog, the new material that I'm releasing, things like that, subscribe to my YouTube channel so that you get notifications for that as well. All right, so let's start with, what are people talking about when they talk about quote unquote shale plays? So this is the definition from geology.com. I won't read it to you, especially the petroleum engineers in the group. You probably can explain this better than I can, but at the end of the day, it's really a type of rock. But shale itself has become a slang terminology for these unconventional type plays. So with these unconventional type plays, what people are referring to when they say shale plays, they're talking about a low permeability formation that is typically less than 5 millidarcies if you're talking about oil, and typically less than 0.05 millidarcies if you're talking about natural gas. It's a consolidated formation, so it doesn't require any sand control. It's typically a relatively stable formation. And it can be shales, but it can be sandstones, carbonates, dolomites, and any other type of rock as well. So it's just any type of rock that's really has that low permeability formation, and it can't produce on its own. So at the end of the day, it's a reservoir that requires multi-stage hydraulic fracturing to be able to produce at economical rates. So the name of the game in these types of plays is to increase your reservoir contact area. So the first way to do that is horizontal wells. So what we're looking at here, we've got our target reservoir, and it really depends on where you're at in the world as to how thick this reservoir may be. So if you're looking at the US and Canada specifically, then typically you're not going to get much thicker than about 500 feet. And they can be as thin as about 50 feet. So let's just assume that 500 feet thickness. You can technically put a vertical well in there. You can get access to that 500 feet. But what if you put a horizontal well in there and then took it out 5 to 10,000 feet? Now you really significantly increase the contact area for that reservoir. The other key factor is multi-stage hydraulic fracturing. So we can take that vertical well, we can technically put multiple stages of hydraulic fracturing in it over that 500-foot period, but you may be looking at 5 stages, a very small number at the end of the day. If you take that 10,000-foot lateral, though, you may be able to place 30, 40, 50, 100 stages even. And now you're really significantly increasing that contact area in your target reservoir. So what are our fracture treatment objectives? So if you're not extremely familiar with downhole completions, don't worry too much just yet. We'll get into this. What we're looking at here, though, this light gray, that's your casing. The dark gray, that's going to be your cement, isolating the casing from the target reservoir. And we've already placed a perforation in the well bore. So we have holes or perforations that have penetrated through the casing, through the cement, and have regained access to our target reservoir. So we're going to pump a mix of fluid and proppant into the well bore. We'll create a fracture, and then we're going to pump that proppant into that fracture to hold it open. So if we zoom in a little bit further, now we start applying pressure. It starts cracking the rock, and we lead into the frac with a with the pad. So this is clean fluid. It's designed to just fracture the rock. Once we've fractured the rock, we're going to then put in our slurry, which is going to be the fluid and the proppant mixture. We pump it into the fracture we've created, and it continues growing the fracture as well. And then once we're finished fracturing, we bleed off the pressure, and the formation will try to close on itself, but that proppant is there in place, and it holds it open and creates that artificial permeability, also known as conductivity. So this allows the permeability, this allows the flow path, and now we produce our hydrocarbon through the fracture that we've created that the proppant is holding open. So why are the multi-stage completions required? We tried this originally in unlocking these reservoirs, what's called a barefoot completion, where you just drill a horizontal well with no real completion in it and try to apply one big frac down it. And the problem is you're going to have path of least resistances due to the drilling stresses, the drilling damage, and also the friction losses. So in this case, what's likely to happen, and what we saw happen in the original experimentation in these reservoirs, is that you had one area of the well that really took most of the frac job and left the remainder of the lateral with little or no treatment. So those are some of the mechanical things that we create and that we have a little bit of control over anyway. But the other thing that we have to remember is this rock is not homogeneous. So there's going to be paths of least resistance just because of the rock properties themselves and formation weakness. So in this case, it'll be the same thing. The fracture will go to the path of least resistance and leave the rest of the well relatively unstimulated. And that's why we divide the well into compartments, what we call stages. So we take these horizontal laterals, we break them up into different sections, and we apply a frac job into each individual section. So these really have been key to unlocking these types of reservoirs. It's not just one technology, it's multiple technologies and techniques, and that's horizontal wells, multi-stage completions, and hydraulic fracturing. All three of those are very critical in these types of reservoirs. And you talk about, what I used in an example was the U.S. plays, but you go throughout the international markets. For example, in Argentina, in the Vaca Muerta, certain sections of it can be 5,000 foot thick. So the original thinking is they could do a vertical well development and have a much cheaper drilling program and get the production. And at least the latest news I've heard out of Argentina is that after trying vertical wells many times, they're just not getting the production. They're not getting quite the isolation just because of the variability over that 5,000 feet. So they're noticing that they need to drill horizontal wells and stay within one type of rock over that 5,000 foot period. So even though the reservoirs so far that we've really kind of unlocked around the world, it really kind of points that we're going to have horizontal wells to complete them. So that leads us into the multi-stage completions. So these are the types of completions that have really, that allow this multi-stage hydraulic fracturing. So the three types that have been proven the most effective and efficient are plug and perf, where you're using plugs and perforations to isolate and divert. Ball activated completion system, where you're using frac sleeves and ball seats to isolate and divert. And the coil tubing activated systems, where you're using coil tubing during the frac job. And in most cases, the most common way to do it is to use a frac sleeve to isolate and divert. So before we get too far into this, I want to familiarize you with some nomenclature if you're not familiar with it, because I'll say this terminology pretty frequently throughout the presentation. So a horizontal well is just like looking at a foot, right? So right at the curve of the well, that's the heel. And then at the end of the well, at total drilling depth, that's going to be the toe of the well. So like I said, just imagine a foot. At the bend is going to be the heel. The end is going to be the toe. So plug and perf. Plug and perf is the original completion system that unlocked these types of reservoirs and is still the most commonly used today. So we have our horizontal well drilled in our target reservoir. We're going to use the drilling rig to run our casing into the well. And that casing is just steel pipe that you connect together and run it as a string. Once you get to the intended depth, you pump cement through the casing into the annulus. And then once you're finished cementing, you do your pressure testing and you move your drilling rig off a location. Once you're ready to begin fracturing, you bring out your pressure pumping crew and your wireline crew. And in this case right here, we've cemented ourselves into place. So because we have cement here at the toe of the well, we no longer have the ability to pump into this well. So in this case, we're going to have through tubing intervention. So we bring out a workover rig or a coil tubing rig. We push down perforation guns. We fire perforation guns at the toe of the well. Those perforation guns penetrate through the casing, through the cement, and re-access the target reservoir. And then once we're finished with that, pull out of hole. And then once we're out of hole, we begin fracturing our first stage. Now, an alternative to this through tubing run is to replace those perforations with a cementable pressure-activated frac sleeve. So you see these interventionless techniques being used more and more commonly just to avoid that through tubing intervention run. So you would run this sleeve, make it up directly to the casing with the drilling rig, run it into the well, cement it into place with the casing, and then when you're ready to begin fracturing, you simply pressure up, and once you apply the right amount of pressure, the sleeve shifts open and you begin fracturing. These sleeves here are also commonly referred to as toe sleeves. So if you hear someone refer to a toe sleeve, that's what they're talking about. So once we finish fracturing our first stage, most operators go to a wireline deployed system because now you have the ability to pump through that previously fractured stage and pump down a wireline assembly. That wireline assembly will include, of course, wireline. At the toe of the assembly, you would have your frac plug. Above that, you have your setting tool, which will set the frac plug and then release from it. And above that, you have your perforating guns. So once you get to the intended depth, the electric signal will be sent down the wire line to set your frac plug. Once you've set your frac plug, your setting tool releases, then you pull up the well bore and to the depth of your first perforation. Once you get to that depth, another electric signal will fire your first set of perforation guns. And then you pull up hole to the depth of your second perforation. Another electric signal fires your second set of perforation guns. And then you pull up hole to the depth of your third perforation, and another electric signal will fire your third set of perforation guns. So remember, it's very important, especially for anyone who's going to be taking the quiz, all of your wireline assembly tools are activated with electric charges through the wireline. So this technique here, this is called cluster perforating. So in this particular example here, we had 3 individual guns. We fired 3 individual clusters of perforations. So the nomenclature here is going to be, we have 3 clusters per stage in this well design here. Once we finish fracturing, once we finish perforating, we pull out a hole with the wireline. Once we get back to surface, we set back up our frac crew and we begin fracturing the second stage. Now after that, the process is going to repeat itself until you've fractured all stages in the well. You shut down your frac job, you run in your wire line, set your frac plug to isolate from the second stage, perforate above that for your third stage, and then you pull out a hole with your wire line and begin fracturing your third stage. Then you run wire line again, set your plug, perforate, and fracture your fourth stage. Pull out a hole with wire line, and this has always really been the weak spot of plug and perf, is that additional wire line run between stages, because that's non-productive time with your frac crew. Once you're finished fracturing all the stages in the well, if this is a traditional plug and perf that uses composite plugs, you do have to enter the well again with coil tubing or a workover rig, mill out the plugs, and then once the plugs are milled out, then you can put the well on production. So another, this is not near as common, but it is ran occasionally in certain applications. You can also do open hole plug and perf. So what we looked at before, we used cement to isolate the annulus, but it is also possible to run open hole packers on the, everything okay? Okay. It is possible to run open hole packers on the, so you run these open hole packers spaced out on the casing, and that'll be your annular isolation between each stage. So overall, the frac job looks the same, except for now you have to be sure that you land your plug and your perforations between your open hole packers, because that's what's going to determine your stage spacing and the length of your stage overall. So once again, it's not very common to set up plug and perf this way, but if you're in certain applications, then you can set up plug and perf this way if you need to. Now let's look back at the fracturing through the clusters again. So when you're fracturing through the clusters, we assume, the basic theory of hydraulic fracturing is we assume that we get even distribution through the clusters. So if you're pumping 90 barrels a minute through 3 clusters, that means your frac design is 30 barrels a minute per cluster. Now the reality is we know that we don't get even distribution through the clusters. So first and foremost, you just have friction between the perforations. So you have to consider that as well. So when we look at it from that perspective, then the path of least resistance is going to be the heel-most perforation, and the path of most resistance is the toe-most perforation. So in this case, we're going to have more fluid distribution through the heel cluster than the toe cluster. And that's where a technique called limited entry perforating comes into play. Now this is a very simple example. There's a lot of different ways to do limited entry perforating, but this is an easy visual to help you understand the concept of limited entry perforating. So now what we've done is we've changed the flow diameter of each perforation. So now the toe-most perforation has 5 holes, the middle has 4, and the the heel-most perforation has 3 holes in it. So now from a flow area standpoint, the toe is the easiest for the fluid to exit, and the heel-most perforation is the most difficult. So what you want to try to do is you want to try to balance out the amount of energy and set it up where each perforation cluster has the same amount of energy required for the fluid to flow out of those perforations. So hopefully, if you do your limited entry perforating correctly, you go back to that even fluid distribution throughout the clusters. But, you know, if you're looking at friction as an example, that's something that we have a little bit of control over, but we don't have control over the heterogeneity of these formations. So what happens, let's go to a 6 cluster per stage example here. And what happens when our fluid distribution looks something like this, just because of the different weak spots in the rock. That's where it gets a little bit tricky. And that's where something called diverters come into play. So these are near wellbore diverters. And if you go through a lot of U.S. operator investor reports, then a lot of times when operators talk about adding more clusters per stage, they often reference something about diverters as well. So diverters, once again, is a little bit tricky. This is a very simplistic example, and it's just giving you the idea of what you're trying to do with the diverters. So the simplest way to visualize it, the simplest way to assume with diverters is you assume that all of your fluid flow goes out of one perforation. So you're going to kind of consider that single cluster of perforations an individual stage. So you pump as much fluid and proppant as you want out of that particular cluster. And once you've pumped that, then you're going to pump enough diverter down to block off the near wellbore for that cluster. And it forces the fluid to divert into another set of perforations. You pump as much fluid and proppant as you want to in that particular cluster, and then once you're finished, you pump another diverter to block off near wellbore there and force the fluid to divert to another cluster. And then you're just going to repeat that process. You would pump however much fluid and volume per cluster that you want, followed by a diverter until you've fractured, or until you've finished that fracturing that stage. Now, the diverters are a couple of different types of materials. So some of them you would have to go in with through tubing intervention to mill them out, to circulate them out. And some of them are disintegrating material that will remove themselves from the well, and you can produce after your clean out run. But let's go back to this example here. Once again, we looked at a very simple example. We assumed that all the fluid and proppant was going out of one cluster. But what happens in this case right here where that's not the case? So how do you possibly do a diverter strategy here? So you pump enough diverter to block off one set of clusters. Well, now it's blocked off one dominant perforation, but there's another dominant perforation. So now does this perforation cluster become even more dominant? And then what happens if the diverter blocks off a non-dominant stage here? Now it's actually doing the opposite of what it's supposed to be doing. And you also have to be careful with your diverter design. You pump too much, then you're blocking off all perforations, and you've created yourself a situation where you've screened out, and now you're going to have through tubing intervention to be able to recover this well and resume your frac job. So diverters right now, we've learned a lot. We're making constant improvements, but overall, they're as much an art as they are a science. And this article right here from the SPE magazine, JPT, is a very good article outlining 5 case histories with a variety of different results with the diverters. So it gives you a good idea of some of the successes and some of the failures with diverters, and just how difficult they really are to get an effective diverter strategy. Now, one of the things you're seeing with clusters right now, or excuse me, with diverters right now, is that operators are using them to eliminate a few stages from the wellbore. So what they can do, this image we're looking at here, this is 2 individual stages with 3 clusters per stage. They could take that same design and make it 6 clusters per stage, and they still have the same stage spacing. They still have the same number of holes and flow area in that stage. And, they may set it up to where they pump half of their frac fluid. They assume that it goes out of half of the perforations, and then they pump enough diverter to block off half the perforations, and then they pump the remainder of their frac job. Now, if you look at these 2 setups, you could, if you're wanting 150 clusters, 150 injection points in the well, the top scenario, you could use 50 stages with 3 clusters per stage to get that 150. And in the bottom one, you would have 25 stages with 6 clusters per stage and still have the same 150 spaced out the same way and everything else. Now, in the bottom scenario, you have half the plugs, so half the plug cost, half the plug deployment time, which is that wireline run between stages, so there can be a significant savings in non-productive time. And then you're also going to have savings on the mill out time as well, because you have half the plugs to mill out. So with the complications of cluster perforating, why do we use it in the first place? Technically, we can do single entry plug and perf. You go in, you fire a single set of perforations, you fracture, set a plug, another single set of perforations and fracture, and then just repeat that process, only fracturing 1 cluster per stage. But the reason we do this is because that would be extremely inefficient. So we do cluster perforating for efficiency purposes. So this is an example here from a prominent Permian operator from their Q1 2016 operator investor report. So in that report, they mentioned that they were using 9,000 foot laterals, 100 feet per stage with 15-foot cluster spacing. So once again, just a quick reminder on the nomenclature. So the 100-foot stage spacing means there's 100 feet between each plug in the wellbore, and the 15-foot cluster spacing would be 15 feet between each perforation within that stage. So what that data translates into, that means they were running 90 stages per well with 6 clusters per stage. And so they had a total of 540 clusters of perforations in that well, 540 total injection points. So if we assume 2 hours of downtime between stages to run our wire line, set our plug, perforate, and pull out a hole, then if we have 90 stages, then that's 7.5 days of downtime, assuming that you have 24-hour crews. If we tried to break that into 540 stages, that would be 45 days of downtime alone. So it's extremely inefficient to try to break it into individual stages when you're looking at this many injection points. So let's stick with that 540 injection point example. There's many ways to set it up. You could do 180 stages with 3 clusters per stage. And if we assume that 2 hours between stages again, that'd be 15 days of wireline time or downtime on your pressure pumping crew. You could do 90 stages with 6 clusters per stage. That would be 7.5 days of downtime. Or you could do 45 stages with 12 clusters per stage, and that would be 3.75 days of downtime. So you're looking at a very significant amount of time and money savings by going with more clusters per stage. Not to mention, you're also in the top scenario, you have 180 plugs that you have to run, 90 plugs in the middle scenario, and 45 on the bottom scenario. So as far as plug upfront costs, there can be some significant savings there as well. Now, not every, everything we've talked about with the inefficiencies with wireline runs, that's talking about a one-off well. So what most operators have done, especially in the US and Canada, where they're going into pad drilling mode, they're able to go with simultaneous fracturing operations. So they start pad drilling, they're drilling these wells really close together at surface. So the wellheads may only be 10, 15, maybe even 20 feet apart. And what that allows you to do is you can go in and set up your wireline and your pressure pumping close enough between the wellheads where you don't actually have to move them. So what we're looking at here, imagine if you're standing on surface, you're looking straight down at the ground. So this, and then we're looking at the laterals. So well A and well B there, those are the laterals that we're looking at. So what this allows you to do is you can fracture on well A while running wireline on well B, and then you can switch those services over. Run wireline on well A while fracturing well B, then switch them over again, fracture well A while running wireline on well B, and then just continue switching the services, and you never have to actually move your frac crew or your wireline truck. So you set up your frac crew with a manifold where it's simply turning a valve to control which fluid or which well the fluid is going into. And then with your wireline, you're just going to set up your crane where it can swing between the two wellheads without ever being moved. So this allows you to start eliminating some of the downtime and being a lot more efficient with plug and perf operations. For reference, it's simultaneous fracturing operations, but it's also very commonly called zipper fracturing as well. So one of the newer technologies with the plug and perf is the disintegrating frac plug. So the concept here is that you don't have to have the mill out afterwards. So you go in, it's just like a standard plug. It's the ball isolated plug. So once you set the plug, you pump the ball down hole, and that's what gives you your isolation. You fracture against the plug, and then once you're finished fracturing, over time with the wellbore fluids, the ball and the plug will disintegrate and leave you with a full diameter. So that helps eliminate that mill out afterwards. You don't have to go in with coil tubing or a workover rig. It gives you makes it interventionless after the frac job, and it also leaves you with a full production diameter. Now, there are a couple of different things to consider with the dissolvable plugs, including price and application and things like that. So right now, you're not seeing a lot of full wellbores with the dissolvable plugs, with the exception of a couple of examples like the Haynesville in the US. But what you are seeing is a hybrid system in some longer laterals. So they'll run the dissolvable plugs at the toe of the well and traditional composite plugs above that. So that way they can go in, they can do their, have an interventionless system at the toe of the well, and then their composite plugs within the operation range of coil tubing, and that interventionless dissolvable plug outside of the range of coil tubing. So then they can go in, they mill out the composite plugs with coil tubing, and over time, the dissolvable plugs remove themselves from the well, and they don't have to worry about extending that coil tubing beyond the distance where they consider it safe to do so. So the second type of completion system is the ball activated completion system. So there's a lot of different ways to set this up, but we'll focus in on the fluid activated packers. So here our open hole packers are going to be fluid activated. We've already got our horizontal well drilled. We've got our completion to the intended depth. And then between the fluid activated packers, we have the ball activated frac sleeves. Once we get to the intended depth, we spot the activation fluid, we pump it through the casing into the annulus, and then we'll set our casing packer once the activation fluid is in the well. Once we've set our casing packer, then we can pressure test with the drilling rig, move the drilling rig off a location, and over time, the rubber on those elements will swell out with the activation fluid and contact the formation to give you that isolation. Now, once you're ready to begin fracturing, you bring out your frac crew, you drop the first ball on the well bore, and because this is open hole, you can pump through the well. You pump it down to the ball activated sleeve at the toe, pressure up, shift the sleeve open, and begin your first stage frac. Now, if we zoom into the second sleeve here, overall, these sleeves are a very simple design, at least from a conceptual standpoint. You have ports on the outside of the sleeve, and if we look at the cutout on the inside of the sleeve, there's an insert that's covering up those ports and has a ball seat profile in it. So as you're as you're fracturing your first stage, you're going to be pumping through all of the ball seats above that. As you finish fracturing your first stage, you're going to pump a ball that corresponds to the second sleeve into the wellbore. It'll land on the seat, isolate from below, open those ports, and force the fluid to divert into the second stage. Now, if we move up hole to the third sleeve, as we're finished fracturing our second stage, we drop the ball that corresponds to the third sleeve. It lands on the seat, shifts the sleeve open, forces the fluid to divert out of the third sleeve. So it's a very efficient fracturing process because you're never actually having to shut down the frac job. Now, it's a little bit difficult to tell in the animation, but the way you have selectivity with these ball and ball seats is the different sizes. So each size gets incrementally larger. So the smallest ball will be at the toe of the well, and the largest ball will be at the heel. That way, the first stage can pass through all of the sleeves above it and only open the sleeve that it's intended to. So after that, you're just repeating the process. You drop the ball that corresponds to the fourth sleeve, pump it down hole. It lands on the fourth sleeve, opens that sleeve, and begin fracturing. Then you pump the ball that corresponds to the fifth stage, and you just repeat that process, dropping the balls in the correct order. And once again, that's really the highlight of this type of system, is that it has nonstop fracturing operations. You may have to slow down occasionally to drop the balls in the wellbore, but overall, you're not having to run intervention between the stages. It's very efficient and very quick at surface. So if we look at the post-frac operations with this system, we're going to produce obviously through the fractures we've created, back through the ports in those sleeves, and then production from below will push that ball off seat and back towards surface. And in a lot of cases now, those are also dissolving balls. So instead of the balls having to return to surface to get out of the wellbore, they'll disintegrate within the wellbore fluids and remove themselves from the well without intervention. Now you can also see that there is a diameter restriction in the production because of those ball seats. So these are designed, at least most of them, with cast iron. They're designed to be compact. So if that production diameter is an issue, then you can go in afterwards, mill out that ball seat, and get a near full wellbore production diameter. Now, even though these were originally designed as open hole completions, they are also available as a cemented completion as well. So you can go in, the overall setup looks the same as far as the frac job. The only real difference with them is that instead of having packers between each sleeve for isolation, now you have that cement. Other than that, when you get to the fracturing process, you're just going to drop the balls in the correct order, and the frac job itself looks like exactly the same. And there are also multi-entry ball-activated frac sleeves. So these are really kind of designed to mimic plug and perf, to mimic that multi-cluster option with plug and perf. So very similar overall with the frac sleeve, with a couple of different nuances. So first and foremost, we have adjustable frac ports. Once again, trying to look like plug and perf with the multiple clusters. So in this case, you can blank out some of the ports if you don't want that much flow area, which allows you to do limited entry techniques. And you can also change the size so that you can have a larger or smaller diameter with those frac ports. Now, if we look at the cutout, once again, very similar. The only difference is now you've got that insert with the ball seat covering up the frac ports. And when the sleeve shifts open, if it is one of the subsiding ball seats, then applying pressure shifts it down. That ball seat will subside out of the way, and the ball will continue moving down the wellbore so that it can open another sleeve in that same stage. So we'll look at what I'm talking about here. And once again, these are more used as a hybrid system in longer laterals with plug and perf. So you run your sleeves at the toe of the well, then you can drop the individual balls. So the smallest ball at the toe, it'll open all three of those sleeves at one time, and then you fracture through all three. Drop the next size ball, you fracture the next three, next size ball, fracture the next three. And now you can mimic plug and perf operations with frac sleeves, but you don't have to run wireline, and you also do not have to mill out afterwards. You can produce through those ball seats. And then once you get to past that point, you do traditional plug and perf with composites. Once you finish with the well, then you would mill out your plugs, produce through your sleeves, and it's the same concept as the hybrid we looked at before. You run plug and perf within the operating range of coil tubing, and the sleeves, the intervention on the sleeves, outside of the range of coil tubing. So a couple of new technologies with these types of systems. So we have the frac sleeves with counter mechanisms. So with these sleeves, all of these ball seats are the same size, and you can see there's a counter. So the toe sleeve is going to be sleeve 0. Once it passes through all the other sleeves until it gets to sleeve 0, and then you apply pressure, shift the sleeve open, and begin fracturing the first stage. Now you drop the exact same size ball again, pump it through all the seats, it'll count down, and now sleeve 0 is stage 2. So it lands on sleeve 0, you apply pressure, shift that sleeve open, and begin fracturing your second stage. And then you drop the exact same size ball again, and now sleeve 0 is the third stage. So with this type of concept, now you're eliminating some of the diameter restrictions, and you have a virtually unlimited number of stages. And there's a lot of different ways to count within these sleeves, everything from mechanical motion to electronics. So another interesting new technology is a ball seat with a collet locator that you pump into the well. So now we have our frac sleeve. We're looking at the cutout view, and instead of a ball seat in the frac sleeve, we have a insert with a collet profile. So you're going to actually drop the ball seat into the well, pump it in, and within the sleeve, you have the collet profile. On the ball seat, you have the collet, and then the ball is actually already on seat, which allows you to pump down the wellbore without having wireline. So you can see here the collet and the collet profile are not the right size, so they don't match up, and it continues pumping down the wellbore. Now as it continues going to the wellbore and it gets to the sleeve with the right collet profile, that collet snaps into place. Now you have your ball seat in the sleeve, you apply pressure, and you can shift the sleeve open, and it's just like the same functionality as the sleeves before. Now you can fracture through that. Fracture through those ports, and then once you're finished fracturing, this is a dissolving ball, so it removes itself from the wellbore. And because you're using the same size ball over and over again, this is a very large diameter ball seat. So you can leave it in the wellbore and produce through it, or if that is an issue, you can go in with coil tubing, run below it, grab it with your tool, and then you pull it out of the wellbore, and that'll get you back to a near full diameter. So the third type of completion system is the coil tubing activated completion system. And the most common way to set this up is the frac sleeves. So we already have our horizontal well drilled. We have our completion system ran into the wellbore, and we're at the intended depth. And once we get to the intended depth, we're going to pump cement through the casing into the annulus, and that's what provides your annular isolation. So these were really designed as a cemented completion with this system. Now, once you finish cementing, you pressure test, then you can move your drilling rig off a location. Once you're ready to begin fracturing, bring out your frac crew and your coil tubing, and then you run your coil tubing in the wellbore, locate your first sleeve, you open your sleeve, and begin fracturing that stage. Then once you've done that, then you're going to pull up hole, locate your second sleeve, open that sleeve, and then you begin fracturing your second stage. Pull up hole, locate your third sleeve, open it, fracture your third sleeve, and then you just repeat that process until all stages in the well are fractured. Now, oftentimes you'll hear this referred to as annular fracturing. And the reason is because you have coil tubing in the well while you're fracturing, and you're actually fracturing down the annulus between the coil tubing and the casing string. So if we zoom back in to look at the operations a little bit more, like I said, you're fracturing down this annulus between the casing and the coil tubing. And when you're doing that, that's actually creating a collapsing force on the coil tubing. So it's actually, because of that force, it's actually trying to collapse your coil tubing. So during the frac job, you're going to pump fluid through your coil tubing. And in most cases, you're not really contributing to your frac in here. But what you're doing is you're applying pressure back against the annular frac and preventing your coil tubing from collapsing. And what that allows you to do also is get a dead leg pressure reading. So what this allows you to do, it gives you a lot better contingency options. So if you do screen out, first and foremost, you can help avoid a screen out because the pressure reading you're getting through your coil tubing, this is a very low flow rate. It's laminar flow. It doesn't have a lot of friction loss. So the pressure you're getting through coil tubing is pretty close to the pressure you're actually getting at the injection point here. Now on the annular side, you've got a lot of friction, you've got turbulent flow. So the pressure you're reading at surface is not actually what you're seeing real time at the injection point. So to prevent a screen out, you can watch this pressure through the coil tubing and back off the pressure or the proppant if you need to. But if it's unavoidable, if you don't catch it in time and you have a screen out to the point where you actually leave sand in the casing, you have a built-in contingency option because you have coil tubing in the wellbore at the depth of the problem with the ability to circulate through the annulus and back to surface. So you can pump through your coil tubing out of that sand jet perforator or circulation sub, and then you circulate that excess sand in the wellbore back to surface. And then once you've done that, then you can resume your frac job. In most cases, moving on to the next stage so that you don't screen out again. So one of the newer technologies for this type of system is reclosable sleeves. So one of the initial reasons you might consider a reclosable sleeve is you can go in, you fracture, you once you finish fracturing, you reclose the sleeve, and then you resume the fracs, you repeat the process for every sleeve. So once you finish fracturing all the sleeves, then you go back in, you reopen them, and you can put the well in production. Now this is going to be a very formation dependent application here. And what you're trying to do is you're trying to prevent the loss of near wellbore proppant. So if your formation takes a little while to close and it doesn't hold the proppant into place, the risk you run when you shut down your frac job and you don't close the sleeve is that proppant just falls right back out of the fractures you've created, and and you lose your near wellbore proppant, and also your near wellbore conductivity is hurt as well. So another option that's kind of interesting with this type of technology is out of order fracturing. So with this, so if you've noticed, everything we've discussed up until now, we're always fracturing from toe to heel because you have to have isolation between each stage. So you can't fracture at the heel and then go below it because then you'll just pump right back out of the heel. But with a reclosing sleeve, we actually have the ability to do out of order fracturing. So just in this example, we'll go back to the toe stage just to fracture your first stage. Once you're finished fracturing, pull the sleeve closed. And now we can go to our third sleeve to fracture our second stage. So we open this sleeve, we fracture our second stage. And then once we're finished fracturing, we reclose it. And now because we've reclosed it and re-isolated it, now we can actually go back down the wellbore and fracture our third stage through our second sleeve. So we can go in, open the sleeve, fracture, and because that sleeve is closed, that's what makes this possible. So now this really the interesting thing to me is that this allows us to start playing with our frac jobs and trying to play on stress shadowing effects and things like that, and hopefully increase the complexity with our frac job and ultimately increase the production. Now, like I said, the coil tubing systems, they were originally designed as a cemented system, but it's really easy to use it as an open hole application as well. So instead of just isolating with cement, then you just put open hole packers between each sleeve to give you that annular isolation. All right, so that's the quick high-level overview of all the completions. So at this point, we've discussed each completion system. Each of them provides effective multi-stage isolation. Each of them has hundreds of thousands of stages. They've been proven to give that effective isolation. Each of them requires different services. Each of them isolates with cement or open hole completion. So once again, pay attention to that point. You can do cemented plug and perf. You can also do open hole plug and perf. You can do cemented sleeves. You can do open hole sleeves. And each of them also, you can divert with multiple entry points or single entry points. You can do single entry plug and perf, or you could do multi-entry sleeves. So how do we choose the right completion system? So let's start with just looking at the benefits and considerations, or at least a few of them. So let's go back to number of stages. With plug and perf, it's virtually unlimited number of stages. It's really dependent on the length of your coiled tubing and the ability to remove and mill out composite plugs. You could also use a workover rig to remove plugs. That'll give you more distance to be able to mill them out. And you can also use the hybrid system that's interventionless towards the toe. So you can use the dissolvable plugs or the cementable sleeves as well. Then you have the ball activated completion system. It has a finite number of ball and ball seats in the original designs. So most of these systems are ran in 4.5-inch casing. So these are the numbers I'm going to use for 4.5-inch casing. So typically, if you're needing a 10,000 PSI rating, you can get about a 40-stage system out of these, excuse me, out of these sleeves. If you can get away with less than 5,000 PSI, you can get up to a 65-stage system. And you also have less than 30 stages if the ball seat diameter is larger than 2 inch. So if you want to restrict that no smaller than 2 inch diameter so that you can get coiled tubing in or that you can cement them into place, then you're in a lot of cases, you're going to be less than 30 stages. Now you also have the new sleeves that we talked about, the counter sleeves and also the collets. And those offer a virtually unlimited number of stages with little to no diameter restrictions. And then you have the coiled tubing system. So once again, virtually unlimited number of stages. Your limitation is going to be the length of your coiled tubing and the ability to function in the long laterals, because you still have to be able to locate the sleeves so that you can open them and function the coiled tubing tools in general. You could also use a hybrid system that's interventionless towards the toe. So you could use cemented ball drop sleeves to extend out the number of stages and longer laterals. Now let's talk about stage spacing. So with plug and perf, if you come across a situation where you have a fault in the well that you didn't really see, then all you have is a casing string in the well bore. So it's easily to pull up hole 200-300 feet, bypass that fault or that geohazard that you've come across, and then just skip over that segment of the well so that you don't have any issues while fracturing. Now with the ball activated system, because you have put it fixed into place where the sleeves and the packers are, then you can avoid it, but you're going to have to skip over a stage. So you drop the ball that corresponds with the sleeve above the fault, then you shift it open and fracture there, and then finish it. So you're going to skip over this section. You still have the ability, but now you have to wonder, well, I wasted money with this sleeve and this packer. So how if I've taken some losses? But then again, it's better than wasting your money fracturing into a fault. And then with the coiled tubing sleeves, you've fixed them into place, you've cemented them into place. So you can skip over that sleeve, go over the fault to the next sleeve, and skip over it that way. Once again, you have a sleeve, you've paid for a sleeve in the wellbore that you're not getting any money out of, but it's better than wasting your time fracturing into a fault. Then we have design flexibility while fracturing. So once again, if you're taking the quiz, I highly recommend paying attention right here. So with the design flexibility while fracturing, with a plug and perf well, it's a cemented casing system. So it gives you 100% complete flexibility on the design during the frac job. You can do whatever you want to in this well, and this has been one of the benefits throughout the years, because in a lot of cases they drill the well and they come back a year or two later to fracture it. So their completion strategy after a year or 2 years may be very different. So when they drilled the well, if this was their original completion design, where they had 3 clusters per stage, but now they go to that 6 cluster per stage design, they can easily do that. They do it on the fly during the frac job, and and can adjust very, very easily. So the design flexibility with the ball activated completion system. So once you've ran the system in the wellbore and set your packers, the completion equipment is set. So that's how many stages you're going to have. That's your spacing on the stages. So there's not a lot to do. You don't have a lot of flexibility if you want to change your completion design. You're going to have to work with what's in the wellbore already. And for the most part, the same with the coil tubing activated sleeves as well, because you've cemented them into place. That's your stage spacing. But you have at least a little bit of flexibility if you run in with a sand jet perforator. So what you can do is you can add stages between the sleeves if you use a sand jet perforator. So mostly fixed into place, but if you set it up, your coil tubing the right way, then you can add some stages on the fly. So your contingency options with plug and perf, if you have a screen out during the frac job, then you have no diameter restrictions above you, so you can enter in through tubing, go in and do a clean out trip of that sand that you've left in the wellbore, and then once you're finished with the clean out trip, you can resume your frac job. So it really just depends on how quickly and readily available coil tubing is as to how long that will take. With the ball activated completion system, if you screen out and you can no longer pump into the well, you can intervene with coil tubing. So you can go in with a profile on your coil tubing that looks like a ball. You can open the sleeve that you want to, or the lowest sleeve that you possibly can, and you can force that sleeve open and resume your frac job from there. So in this case here, this isn't too bad because we screened out on one sleeve. We would have to skip over one, but we're only losing one stage, so it's probably worth it. The problem is what if you have 30 stages below where you can open? Then you really have to look at it and say, well, am I willing to lose 30 stages? Now, if that's the case and you don't want to lose 30 stages, which in most cases you probably wouldn't want to, then you can go in, mill out the ball seats, and do an open hole plug and perf. So it's not a complete loss of the well. It's very inefficient, as you can imagine, but it is possible to recover. And then like we talked about, hands down, it's the best with the coil tubing activated system, because you already have that built-in contingency with coil tubing in the well at the depth of the problem, with the ability to circulate through a sand jet perforator or a circulation sub, and you just circulate it out, you move your frac onto the next stage. And operational efficiency. So from plug and perf, if you're using it, especially on a one-off well, it can be very tedious and time-consuming, depending on how good your frac crews are and what depths you're dealing with. But you're going to have to pump in between stages. You have to shut down, run in your wire line, set a plug, perforate, pull out a hole. And, in most cases, if it's a really good frac crew and wireline crew, that might be 2 hours. But, I've heard nightmare stories of 8 to 10 hours per stage. So there's a lot of variables there. But remember, the simultaneous fracturing operations, also known as zipper fracs, those also can help dramatically once operators go into pad drilling mode and they have the option to set up your wireline and coil tubing and then just rotate the services so that you're minimizing the non-productive time with wireline and the non-productive time with pressure pumping while you're running the other services. And they can also apply this on a large scale, bring out multiple frac crews. Excuse me. Bring out multiple frac crews and multiple wireline crews. And some operators report that they've got it down to such a process that there's virtually no downtime between stages. So they've gotten plug and perf very, very efficient. Now with the ball activated completion system, this is really one of the highlights because you're just dropping balls, opening sleeves, fracturing, and you never have to shut down that frac job. You just continue that nonstop fracturing process. So very, very efficient with surface efficiency. With the coil tubing activated system, it's pretty efficient, but there is a little bit of downtime between stages because once you finish fracturing, you have to pull to release the packer. You have to go up hole, you locate your next sleeve, open it, and then you resume your frac job. So once again, it depends on how good your crews are. It depends on the depths that you're dealing with, but you may be looking at 10 or 20 minutes between stages to move your coil tubing and open the next sleeve. And you also have to consider services required for fracturing. So pressure pumping, all three systems have to have it, obviously. Wireline, you have to have it with plug and perf. Coil tubing, you may have to have it with plug and perf, depending on how that toe stage is set up, and if you have to do a tubing conveyed perforation run on the first stage. And you obviously have to have coil tubing there. Now, there's additional considerations for that too. Are wireline units available? I know a lot of international people are attending right now, and that's where I've seen it. If you go to most U.S. markets, wireline units are pretty readily available, but I've been in a lot of, especially emerging markets with these, where the wireline units weren't available, or they had equipment shortages on certain things. One of the situations I saw in the past is, are perforating guns accessible? One of the countries in North Africa, we were looking to do plug and perf, and we could not get perforation guns through customs. So that wasn't available. Also, is the right size coil tubing available? Because it's going to be pretty tough to mill out plugs if you don't have the right size coil tubing, if you can't get it to location. And, another important thing, are the well sites accessible to coil tubing, especially in plays that are located in mountainous regions. Coil tubing units can be relatively bulky. So can you get that right size coil tubing up to the well site? And, the alternative is a workover rig. So is a workover rig available, and can it get to the well site? And you also have to consider, what are the costs of these services? Sometimes the costs can be all over the board. I remember, it's probably been a decade ago now, but comparing some costs in Oklahoma, it was $40,000 a day for a coil tubing unit, but in California, it was $120,000 a day for a coil tubing unit. So all of those play a huge factor in economics and break-even cost on the well. So this is just a chart side by side. If you want to know more, like I said, we limited on time, so we couldn't cover everything, but there's a paper out there, and you can also catch all of these on my video blog as well. So we'll start wrapping things up here with just a couple of quick examples of how to compare some of the systems. So let's make a couple of assumptions here with an extended number of stages. So let's assume we have a 40-stage frac job, 1 hour per stage in the frac plan, and no operational issues. So if we use the ball activated completion system, that means it's 40 hours total time to stimulate, because you don't have to shut down your frac crew. So that's 2 days with a 24-hour crew, 4 days with a 12-hour crew. Now, if we did the same system with plug and perf, we have to make that additional assumption of the runtime of wireline to set the plug, perforate, pull out a hole. So let's assume it's 3 hours in this case. That would be 160 hours total time to stimulate. That's 7 days with a 24-hour crew, 14 days with a 12-hour crew. So in this case, your total savings with the ball activated sleeves, you're talking about your frac cycle time going from weeks down to days. But, let's look at a small number of stages. And you still see that this is not as common anymore. You do see it in some emerging markets right now. But let's do a 5-stage job with the same assumptions. So with the ball activated system, 5 hours total time to stimulate, 1 day with a 24-hour crew, or a 12-hour crew. Plug and perf, that same 3 hours assumption between stages. That's 20 hours total time to stimulate. That's 1 day with a 24-hour crew, 2 days with a 12-hour crew. So in this case, it's virtually the same. You really have to look at the local economics and what's available and what the cost of those things are to be able to compare these two systems, because from a surface efficiency, there's not a lot of gain either way. And so if you follow completions, that North American trends, in the US specifically, plug and perf is over 95% of the market. But I always caution people, because that really took hold when the downturn hit. Before the downturn, it's a tough number to keep track of, but going back to 2013 and into 2014, plug and perf was probably 60% of the market. But it's all relative to the downturn and how the effects of a downturn on completion decisions. So it's first important to understand how most U.S. operators are structured. First, you have the drilling AFE. So that's everything done with the drilling rig. You have the completions AFE, which is everything done between drilling and production. And then you have the production AFE, which is everything done after the completion. Now, what's interesting is the drilling AFE, everything that's done on the drilling rig means you're constructing the wellbore on the drilling budget. So part of the downhole completion cost is actually on the drilling budget. So, you know, if you're wanting to run frac sleeves, then you're putting it on the drilling expense because it's ran in with the drilling rig. So we'll look at the U.S. side of the Bakken. So in 2015, or well, 2014, before the downturn hit, the state of North Dakota gave operators 1 year between drilling the well and fracturing it and putting it on production. When the downturn hit, they extended that to 2 years. So operators could drill the well, hold it in place for 2 years before they had to fracture it and then put it on production. Now, there were several prominent Bakken operators that publicly stated that they would continue drilling so that they could hold their acreage, but they would not be fracturing and producing the wells until they saw oil prices they liked or until the 2 years was up. So let's look at how that affects the overall drilling budget. So we'll break down each of the completion costs first, and these are estimated numbers. You know, it's going to vary obviously by your region, the shipping, all sorts of different things like that. But these are just example numbers that you can use it kind of as a guideline for your example. So casing, each completion requires virtually the same amount of casing, so you're not seeing any significant difference there. If you were going to cement the 10,000 foot lateral, that might be $50,000. If you were going to run, and we're doing a 50-stage system here, right? So 50 ball activated frac sleeves. If you assume $3,000 each, that's $150,000. If you ran 50 open hole packers and assume that they were $3,000 each, that's $150,000. And if you used 50 coil tubing activated sleeves and assume that they're $3,000 each, that's $150,000. So what does our wellbore construction cost look like for each system? A 50-stage plug and perf would be $50,000 because you need the cement in the wellbore. A 50-stage open hole system, open hole ball activated system, would be $300,000 for the sleeves and the packers. A 50-stage coil tubing activated system would be $200,000 because you need the sleeves and the cement. A 50-stage open hole coil tubing would be $300,000 for the sleeves and the packers. And if you wanted to do a 50-stage open hole plug and perf, that would be $150,000 for the packer. So looking at this number here, I mean, it's, you know, if the operator's strategy is to drill but not complete, plug and perf is the clear choice. I mean, you're talking about saving millions of dollars in less than 10 wells just on the wellbore construction cost. So in a time when cash is critical and you need to keep your cash, then plug and perf is the obvious choice here. Now, something interesting that I think was largely by accident, but it played out really well. 50-stage plug and perf is not a 50-stage plug and perf. It's whatever you want it to be. It's just a blank casing string. So if it's 100 stages that you want to run now, you can do that. If you double the number of clusters and only do a 25-stage plug and perf, you can do that. So, you know, especially if you're waiting 2 years, a lot can change with your completion strategy. So that's the other benefit of running just a blank casing string into the wellbore. So that's it for my presentation. Thank you, everyone. Like I said, I know this is a very quick overview. There's plenty of free resources on my website out there and my YouTube channel, so be sure to check those out. And we will go back to question and answer.
Thank you so much, Aaron, for the great presentation. Everyone loves it, and we have like lots and lots of questions. I would like to take, for the sake of time, I'd like to take around 3. So the first question is a bit on the longer side. The person is saying, what is the most effective spacing between wells during fracturing? And he's also asking if the frac growth from one well prevents the frac growth from another well.
So it's a great question, and honestly, it's kind of a to be determined question. So there's still a lot of experimentation going on with stage spacing within a well, and also well spacing within a field. You know, frac kits have become a really common topic that everybody's looking at, and it's not fully understood yet. So it's going to have a lot of variation between each play, obviously, because of just the different rock properties. And at least what I'm hearing from most operators, there's actually quite a bit of variability within the same play, just because if you go to certain sections of the field, that rock property can vary quite a bit as well. So yeah, it's kind of one of those things where it's a lot of trial and error. You know, we're consistently updating our models, calibrating our models, and you know, we're still learning a lot with unconventionals.
Great. So another question, why there is a limit for coil tubing for milling blood?
I'm sorry, could you repeat the end of that?
Yeah. So why there is a limit for coil tubing for milling plug?
Oh, I got you. Yeah. So, well, so coil tubing, it does have a finite reach, well, and a finite distance as well. So, once again, it's going to depend exactly where you're at. I'll use U.S. examples just because that's what I'm most familiar with. But if you look at most of the Department of Transportation requirements for the U.S. highway system, then the most you really can do a coil tubing unit is about 26,500 feet. So there's a finite limit on the actual length of the coil to be able to transport it across the roads. And then once you use that coil, you're going to have fatigue. So you might have to cut off 100 feet at a time, 1,000 feet at a time. And so once you've started using that coil tubing unit and it's down to maybe 15,000 feet, it can't get out in some of the longer wells. Now, the other issue, and the primary issue, is going to be the ability to transfer weight because you are in a horizontal well. So when you're in that horizontal well and you're trying to get coil tubing to the toe of the well, you're going to have a lot of friction coming across this curve here. So that's going to take away and make it difficult to actually get the weight on bit to the bit that you're at. And then in the vertical section, that coil tubing is also going to be buckling. So it's difficult to actually transfer the weight into the wellbore and at the bit at a certain point in time. Now, we've gotten really good at that over the years. Just to kind of give you a generic example, what we've done with the improvements with agitators, with the fluids, the lubricity, some of the wells where we couldn't get more than 5,000 foot in the lateral 10 years ago, even 5 years ago in some cases, we can extend past 10,000 feet in the lateral now if we have the coil tubing. So a lot of improvements in that overall throughout the years, but and now you see workover rigs becoming a lot more common in the U.S. too for milling out plugs.
Okay, another question. How may the friction forces affect negatively the overlap of the penetration while drilling?
Sorry, could you repeat that one more time?
Sure. How may the friction forces affect negatively the overlap of the penetration while drilling?
I'm sorry, I'm not sure if I understand that question. That sounds more like a drilling question anyway. So
yeah, me neither. Me neither. Okay, let me see if we have another one. Okay, there's a simple question that is repeated several times. And using Frac plug, how can we push the ball down in a horizontal well?
Yeah, so it's just pumping. You're pumping it with fluid. So these are composite balls in most cases. So they're lighter specific gravity than some of the ones that you might be used to, especially in conventional applications where it's vertical. You would just use the heavier balls. Most of the time, you'd even let them sink for 30 minutes, and they would just gravity feed in a vertical section. But obviously, it's different in horizontal. So what you're going to do there is you would actually set the plug, pull out a hole with your wire line, and then you drop the ball in the wellbore, and then you just pump it with the fluid. So you're going to pump it at a certain rate to be sure that it is moving down the wellbore. And then once it gets on seat, then that's what provides your isolation. And the alternative type of plug, and once again, we didn't have time to cover everything, but you can also have a self-isolating plug so that you don't actually have to pump the ball in the wellbore. It's actually just installed on the plug itself. So in that case, you wouldn't even have to pump the ball down. You would actually have the ball already in place. Hands down, most commonly though, it is the ball isolated plug where you do drop it down in the well and pump it.
Okay, another question related to the ball and sleeve. How can the ball into the sleeve be removed before production stage?
So it can be a couple of things. You could flow it back to surface in some cases. Anyway, so you could potentially flow it back to surface. If it is an issue and you're concerned about it, then you can also use the dissolvable balls so that they'll dissolve in the wellbore fluids and you don't have to worry about it. And, at least a lot of times the testing that's done, they at least try to get balls that you can mill out as well. So there's a couple of different options. Ideally, though, you either flow them back to surface or you use the disintegrating balls to fracture. Now, what's kind of interesting there is that in most cases now it is the disintegrating balls because those are alloys. So most of those are magnesium alloys, and they actually are stronger than most of the composite materials. So in a lot of cases, just over time, they should disintegrate and remove themselves from the wellbore.
Great. Well, that's it for today. Thank you so much, Aaron, for your presentation and for your time. Thank you so much, everyone, for attending, and see you tomorrow. Thank you.
Sounds good. Thanks, everybody.